Okay, so we're going to have our first attendance quiz today. Be ready. It could be in the middle of class or the end of class. And it has to do with stuff we're talking about today. So be ready. Be ready. Listen. Take good notes. So here we go. Oh, let me see. Just want to talk about something briefly here. To make sure we got it. So suppose, in terms of surface area, suppose I got just something easy, x squared. Okay, I'm going to revolve that about the x-axis. And so we'll get like kind of like a Hershey's Kiss, okay, like a Hershey's Kiss. And for surface area, we're talking about like the lateral, the side surface for that Hershey's Kiss. Okay, and so say I want to write a surface area function from 0, and I want to do it in terms of x. Okay, so what do I need to do that? What do I need to write a surface area accumulation function in terms of x? So like I'm going to do, break up the x-axis into delta x intervals. I'm going to imagine x increasing through those delta x intervals. What do I need to write the surface area function? You should all be thinking, I need the rate of change of surface area, right? So it's going to be the integral from 0 to x of rate of change of surface area, t dt. Okay, so that's every quantity that we want to write a net accumulation function for. We say the same thing. We want the rate of change of that quantity, and then we can set up our integral net accumulation function using that rate of change. Okay, so what is that? So what was the rate of change? So rate of change, surface area in terms of x. That was our 2 pi r times ds. And that was the square root of 1 plus. So it's going to be the, f prime, 2x. You can say f prime 2x squared. And so the question is, really the big question is, what is r? What is r? So r comes from, you got to draw these pictures. So r comes from, think about in each interval, what's happening? We're going to start, it's going to show up the best here. I'll try red. Should have made it bigger. I'm going to make it bigger. This is too small. Okay, so think about what's happening in one particular delta x interval. What's happening is we are accumulating surface area, and so that is according to these little ds segments, right? ds, which starts tangent to the curve at the beginning of the interval, and that little ds gets rotated around x just like the curve did. Okay, so it looks like this. And that's our little ds right there. So you have to imagine these it's called we call them ribbons, right? These ribbons that have the angled edge that's following the curve, right? That's tangent to the curve. Okay? And so the 2 pi r is for that leading boundary, right? That leading boundary right there. And so that means that r is this radius right here. So what is that radius? So every time you do a surface area question, make this kind of picture. Draw a typical ribbon. Imagine them increasing in your intervals. Okay, And so what is r? Is our x-coordinate, y-coordinate, big variation in x, big variation in y? So from here to here is radius. So what is that? Y-coordinate, right? It's the y-coordinate to the curve. Okay, so when I write this rate function then, if r is y, this is y, do I need to change that or not? What do I need to change it to? What is y equal to in terms of x? X squared. Okay, so then my rate of change function becomes 2 pi x squared times square root of 1 plus, and then derivative 2x. Derivative of x squared is 2x. So there's my rate function that I can use to write my net accumulation of surface area. Okay, now I want to do the same surface, the same Hershey's Kiss, but I want to do delta y intervals. Okay, so I'm going to let y increase through delta y intervals. But it's the same surface rotated about the x-axis. So I've got my little beveled edge. So now I'll do blue here. So I got my little beveled edge. So now it's delta y intervals. Are those typical ribbons going to look like that? Or are they going to now look like this? Red or blue? So when I'm doing delta y intervals, I still have the same surface rotated about the x-axis. Will my ribbons look like red or blue? So I'll finish the blue one here. Will the ribbons that generate or accumulate surface, will they be red or blue? The red ones or the blue ones? Oh, I stumped you there, I guess. So the blue ones would accumulate surface for, if that thing was rotated about the y-axis, it would be like this bowl. Is that the same? No, right? So taking that ds around the y-axis and then letting those increase this way would create like a bowl surface. So even though we're accumulating in delta y intervals, we still are using these same ribbons because of the axis of rotation. Okay, so that's a little different than volume. With volume, when we changed the variable, we got a different kind of cylinder that was filling up the shell. Remember that? But when you change the variable with surface area, you end up, if it's the same surface, you still have to have the same ribbons based on the axis of rotation, regardless of what your variable you're choosing is. Does it make sense? So now, in terms of y, the rate of change of surface area in terms of y, it's still 2 pi r. And what is r? Still y. And now we need what? We need y, or we need x as a function of y. So if f of x is x squared, then what does x equal? Square root of y. So that would be a like say g of y function, right? So x as a function of y. So now we have 1 plus g prime of y squared under the radical. Okay, whereas this is now the writing x as a function of y. And so then the question is, what is that in this function? So we need to write this in terms of our independent variable y. So what is it? Do I change it to x squared or square root of x or square root of y? No, it's just y, right? So this is already in terms of y. It is the y coordinate, the radius, and we're writing it in terms of y, so we're done. So this would be the rate of change in terms of y. If we're generating the same surface as before, the Hershey's Kiss, but using delta y intervals. We use the same shells, but now it's still y. The radius is still y, but now in terms of y, you're done because y is in terms of y. So here are your two rate functions. in terms of x, in terms of y. Both, the radius is always y. It's just you got to get it into the variable of your independent variable. So that means x squared if it's x. That means just y if it's y. Okay, does that clear it up? See, question?
When you're defining this in GC,
Yeah.
the first one, you put R S of A. Would you have to do R S of A, R S of A x equals 2 pi? I'm just confused why the very top one has an A.
Because I just didn't write it. Yeah, whatever in GC, whatever you call it, you have to call it. So I just forgot to write the A.
Okay.
Yeah. Yeah, in GC, you have to be consistent. Whatever you call the function, if you're going to use that function, you have to call it by the exact same name. Okay, other questions? Okay, so this one is due, I think, Monday at 5, the surface area homework. The next one, the online homework, is Monday at 5. And then there's a 2-page written homework. Also, maybe due Monday or Wednesday next week that has to do with arc length and surface area. So just look for that on Canvas. I'll post it probably today. But draw these pictures. It's all about, so getting these rate of change functions correct for surface area is all about getting the right picture, getting the right radius, depending on which variable you're using. Draw the pictures. Okay, so let's change the subject here a little bit. We're going to talk about quantities of motion. Quantities of motion. We've been talking about a lot of geometry quantities, right? So signed area, volumes of revolution. What was the next one? Arc length and surface area. Those are all kind of geometry quantities. Now what about quantities of motion? So here's the space shuttle, the program that's been discontinued back from the 80s and 90s, the space shuttle. And so here's the velocity of the space shuttle every second after takeoff. Okay? At 0 seconds at takeoff, it hasn't started moving yet, and then in 1 second, it's 30 meters per second. And this is close. I think it's something like 29 or something, 29.5 or something. So, but just to make it easy, I just called it 30. So what do you notice about the velocity? What do you notice about the velocity when you look at that table of velocities? What about 30 meters per second? Is that always the velocity? Every, good. All right, so he's saying it's increasing by 30 meters per second every second. Okay? So, what is that? Saying that it increases by 30 meters per second every second. What is that really talking about? What kind of concept is that? More generally? What's the magic word? What's our big topic in this course? Isn't that the rate of change, right? It's the rate of change. Rate of change of velocity is? (30 meters per second per second). So I want to describe this in a broad way, in a good way. So what does it mean that the rate of change of velocity is 30 meters per second per second? I've asked this question many times this semester. Started talking about it in the first week and have asked it probably a dozen times since. What does it mean that the rate of change of velocity is 30 meters per second per second? Everyone's talking to somebody. Tell the person next to you. What does it mean that the rate of change is 30 meters per second per second? Okay. Is it true? Every second the space shuttle's velocity increases by 30. Is it true? It's true. Good definition? Broad? Meaningful? No, that's what you would have said before you were in this course, right? But now we know something much stronger than that. Much stronger than that. So tell me your name in the red shirt. Yeah, Connor. Okay, so you're saying given what? Given any, not quite a time value, but a variation in time, right? And what do we call that variation in time? Sure, we'll call it dx. What do we know? Given any variation in time, what do we know? What's that? And what does y mean? The variation in distance? This is the variation of velocity. So the variation in velocity is 30 times dx. Okay. Yes, the speed goes up 30 meters per second every second, but you know a lot more than that, right? I've said this before many times. You know a lot more than that. You know how much the speed goes up? What? In any variation of time. How much does the speed go up in half a second? See, you knew that. How much does the speed go up in 2 seconds? How much does the speed go up in 10 seconds? 300. How much does the speed go up in 1/10 of a second? See, a constant rate of change tells you a lot more than just what's happening every 1 second. It tells you what happens in any variation of time. So in any variation of time dx, the variation in velocity is 30 times as much as that. And so that's our dy equals 30 dx. Where y, this is our variation in velocity given any variation in time. Okay, is today the day? Is today the day we all get it? Doubtful, but we'll keep trying. We'll just keep trying and trying and trying. Rate of change tells you a lot more than just what happens in the variation of that. It tells you what happens in any variation of the independent variable. Okay, it's going to stick soon. Okay, so we're going to use that fact. So I want you to predict the velocity at 4.7 seconds after takeoff. But do not make dx 4.7. Not allowed. Not allowed to make dx 4.7. Okay? So I want you to predict the velocity at 4.7 seconds after takeoff. But this is not allowed. Don't make your dx 4.7. Okay? Go. So how would we predict the velocity at 4.7 seconds after takeoff? So for instance, 4.7. What will the velocity be? How can we use this idea of constant rate of change to predict that? Oh, use dy equals 30 dx. It's so much easier. Use this, right? In any change of time, you know how much the velocity changes, right? How can you use that? Use the one that's going to help you the most. In any change of time. Okay, is it Paige? How'd this go? Oh, Sage. Sorry, Sage, right? Sorry. Okay, so how can we use what we just talked about? How can we use, is there a good change in time that would be strategic here to help us find what the new velocity is at 4.7? Yes, sir?
I used the table, so at 4 seconds it's 120
Right.
meters per second. And I use 30 times 0.7 because it's 4.7.
So this is like a dx of what? 0.7. And so that tells us what?
That there's like a variation of 0.7, so I use 30 times 0.7 to get dy, which is 21.
So dy is going to be, so given that change in time of 0.7, the corresponding change in speed would be 30 times 0.7, which is 21. Okay, and then?
And the velocity at 4.7 seconds is 141 meters per second.
And that came from what? How the 141 came from? 120 plus 30 times 0.7. Because we can, now that we know that the rate of change is 30 and we've got a change of 0.7, the change in velocity will be 30 times that change, or 21, and then we can just add that to the 120. Does this look familiar at all? 120 plus the new amount of change? What does that look like? Someone said it. Total accumulation, right? What's our total accumulation? All the accumulation from before plus the change, right? The change since that amount, right? So it's like this is kind of like our total accumulation function. All the accumulation from before, which would be like v of 4, plus the new amount of change since then, right? Since then, which is the 30 times 0.7. It's just we had an integral function here to actually calculate like the velocity at every, right? So the velocity at every. So let's do that. So now how could I write, I got v of 4.7 equals 120 plus that. So how could I write now at a total accumulation function v of x? And say starting from, I want to use v of 4 as my starting point. Then I would write what? Plus what? I want to be able to get any velocity now after 4. So how do we write the net change since 4? Integral? Oh, and I want to use my new notation, right? What's my new notation here? So this would be 4 comma x, right? Starting from 4. This is the 2 argument notation, starting from 4 to x equals 120 plus 4 to x of, what am I looking for here? The rate of change of velocity, right? And what is the rate of change of velocity? 30 times dt. All right. But this is a really easy function. If I wanted to write v of 0 of x, do I really need an integral? How do I get the velocity for x seconds after 0? What do I do? So if 1 second gives 30, 2 seconds gives 60, 3 seconds gives 90, he wants 30 times x. Agree? Well, that would be starting from 0. Okay, so a big topic or a big theme today is here's 2 functions, and these 2 functions have different forms, right? They're both velocity functions. One difference, of course, is this one starts at 4, this one starts at 0, but that's not the difference I want to focus on. The difference I want to focus on is this one. Because of the integral right here, this is called a function in open form. So there are other types of functions that are in open form or expressions in open form, but an integral, Our net accumulation functions are an example of open form. What does open form mean? Open form means it reflects the process. It reflects meaning. Remember, we spent the whole first 4 days of class building this from the ground up. And this still reflects that whole journey, that whole 4 days, right? What is 30 times dt? What is that, essentially? mdx, right? That's a little bit of change in velocity, in this case, calculated by the rate times the change. And what does the integral symbol mean? Remember what that stands for? Accumulation, summing up, right? Summing up all these little accumulations or little variations in velocity. So 30 times dt gives me a little variation in velocity, and the integral means sum all those up, starting from 4. So see, there's all this meaning packed into that, right? It explains exactly what's going on. So this reflects meaning and process. But what's the disadvantage to this form? There's a disadvantage to this. What's that?
You can't find anything below 4.
Okay. Yes, sir. It's lengthy. Good. Was there another hand in the back? Yeah. Right. So like we had to. How did we get values of the velocity function in this form? What did we do? How did we were able to get values of this? Please know this. How did we get values of functions written in this form? What do we have to do? We're doing it all semester. We already did. So now I have this function, and I want to get, what is, say, v of 4 comma 6 or v of 4 comma 8? What do we do? GC. We had to use technology. We had to put that in GC and let technology do the heavy lifting of getting velocities for us, right? Every single time using function notation. So what it doesn't compute values easily. It requires technology. All right, so we had to type that into GC, and then we have to use function notation to generate values of, in this case, velocity for different values of time. And that's great. That's why we spent 4 weeks on it, because we're really thinking about the process and the meaning and what the symbols mean. Okay. So then, on the other hand, this is called closed form. So closed form, it does not reflect this meaning of bit by bit accumulation of changes in velocity. But what is its advantage? What's the advantage to this velocity function, the fact that it's 30 times x? What's that? Easy to compute. And we can even do it in our head. I could just give you values of x and boom, boom, boom. It would you'd just be spitting out values of velocity without even using a calculator. Okay? So this is computes results quickly and efficiently. That says quickly and efficiently. That's closed form. So closed form is like most of the functions you've been dealing with in your math career. Polynomials, sine and cosine, exponential functions, logarithmic functions, and combination, all in arithmetic. So any addition, multiplication, subtraction, division, like I said, exponents, logs, all these functions that you've been dealing with your whole math career have been closed form. It's now when you get to like an integral function or like a limit function with limit in it. Okay, those are the ones that reflect process and don't calculate efficiently or quickly. You need technology. Okay, So both have their advantages. Okay, and in a week or two, we're going to start learning, given open form, right? We've been writing everything in terms of open form or accumulation functions. We're going to learn techniques to figure out the equivalent closed form. Okay, so that we're going to spend a whole section of the course for techniques for finding the closed forms from the open form accumulation functions. So that's coming up soon. Okay? So to write velocity, we needed rate of change of velocity, which was the 30. And what's another name for that? Have you been thinking it? How much the speed goes up given any change in time. What is that called? Speeding up, and you're in a car. Speeding up is acceleration. So this 30 meters per second, that's the acceleration. That's the rate of change of velocity. Okay, questions on this stuff so far? What open form is, closed form? Either in the middle of class or at the end of class? Here we go. So I got two. These are acceleration functions. I got some questions for you about these acceleration functions. Which car is moving faster at 2.5 seconds? And when will the cars have the same speed for the first time? Just those two. First two, just take a minute to talk about those questions. These are acceleration. So this is seconds, and this is feet per second per second. Okay, what do we think? So here's 2.5 seconds right here. So which car 1 is blue, car 2 is red. Which car is moving faster at 2.5 seconds? What do you think? Car 1 or car 2? A few people up in front are saying car 1. What do you think? Agree with that? Car 1. Why car 1? Look at car 2's graph is higher here. What's that? It's acceleration. So how do we think about getting variations in speed, right? Accumulation of variations in speed. We think about like little intervals, right? Say in this interval right here, how would we get the variation in each car's speed? In that interval. Yeah, mdx, exactly, right? This is acceleration, so it's the rate of change of speed. So you think about at this speed over that amount of time versus the car 2 at this speed down here over that amount of time. I should have made bigger intervals. So thinking about over this little change in time, say dt, this car's rate is down here, and this car's rate is way up here, bigger than 1. So which car is going to accumulate a bigger change in speed in that interval? Car 1 or car 2? Car 2, it's mdx, mdt is a lot bigger than the mdt for this one down here. And that's happening all through this time period that car 1 is going to accumulate much bigger changes in speed, right? And now it flips, and now car 2 is accumulating bigger changes in speed because it has a higher acceleration, but not enough to overtake all that happened in the first 2 seconds, right? So when would you just eyeball guess, when would cars have the same speed for the first time? No, after 0. So same speed for the first time after 0. We don't even know it's 0. This doesn't tell us what the speeds are at 0. Okay, so one of the cars could have already started, and this is acceleration, right? The acceleration is 0 at 0. So when along here would you expect the cars to have the same speed for the first time? Someone said 5. What do you think about 5? Yeah, maybe so. Maybe somewhere in here, right? Because car 1 is going to have a much faster speed. Even here, car's going to have a faster speed. And then it's going to accumulate even more speed. So for sure at 4, car 1 is going to be going faster. But then starting at 4, car 2, its acceleration is much higher than car 1. So somewhere, maybe somewhere in here, 5 or 6 seconds, car 2's speed is going to reach car 1's speed. How can we find out exactly when? I want to know exactly when. How can I find out? Got this amazing tool GC here. How can I find out exactly when their speeds are the same? What can I do? How can I find the car's speeds at any time? Either one of those cars. Exactly. Yes, please. So arc length. Is arc length the length of the arc? Is that going to help us with speed? Not quite. Yeah.
So
Is that
their total accumulation equal to each other?
their total accumulation? How do I get their total accumulations? How do I get those? I'm just staring at acceleration graphs. If I want to get exact values of velocity, what do I need? Yes, sir. But how would I get that? Even if that, so I don't want to focus on area because that's not really the quantity we're focusing on. But even so, how would I get that? Yeah. Oh, you just scratching your head. To do what? And how do I know that? How do I know how fast the cars are going at a given moment? Exactly. With what? I got to write velocity functions. I got to write velocity functions, right? So how do I do that? How do I write the velocity function of car 1? See the net accumulation function is how I can get exact values of velocity rather than eyeballing it off of a rate of change function. So how do I write the... What's that? Okay, antiderivative. Integral, right? Integral, right? Accumulation. So I've got the rate of change, which is acceleration. I want to write the velocity, so that's net accumulation is our integral, right? From, so I'll do A, and I'm using T now, so A to T. Okay, what's my rate of change? I can see, so these are the two rate of change functions, so I got A1. So this is going to be from A to T. And then what about this, A1 of T? You do something else, so I'll use U. Usually we use X for like the independent variable. So yeah, we could have used X, but let's use U. So I got there's my velocity, got the accumulation function, 1 for velocity 1, and then similarly, but this needs to be A2. Okay, so I got those accumulation functions, and I want to know when are the speeds going to be the same for the first time. So what should I do? Okay, what's the problem with setting them equal to each other? What kind of form is this? Open form. Now I got two open forms set equal to each other. I'm going to solve that, right? So that's this again. This goes back to the disadvantage of open form, that it's not about easy computation, right? We'll see. We can set these integrals equal, but it's like, how the heck are we going to get the t that makes them equal? They're both in open form. So what's another vehicle we have here to figure out when they're the same? Right, graph them. Awesome. If we graph them, what will happen? So here's we can graph both, and I'll put them over in the right-hand pane. And so now here are those two velocity functions graphed. And so lo and behold, what we got? We see, like we said, car 1 has a higher speed all the way until 5.68. That's what we said. So we said something between 5 and 6. At 5.6875 seconds, car 2 catches up in speed to car 1. So now they're at the same speed. So who's ahead? Are they at the same place? Or is one car ahead at 5.6875 seconds? Are they the same place? Yeah?
Car one's still ahead, they just have the same speed.
Yeah, so right. Now look, same thing again. Car 1 is way ahead. It's been going at a higher speed this whole time. It's just now that the speed of car 2 is now the same as car 1. But car 1 is still ahead. Okay, so we'll have to pick this conversation up on Monday.